Welcome. The topic we'll be discussing in this lecture is DMA, Direct Memory Access. So we are discussing about IO module. So in the last two lectures we have discussed about programmed IO and interrupt driven IO. With programmed IO and interrupt driven IO, processor should be involved in the process of IO operation. Okay, that is, if you take programmed IO, the processor should initiate the IO operation by issuing an IO command, and it should wait until the IO operation is completed. Once the IO operation is completed, it should read that particular data from the IO device by placing a request to the IO device that I need the data. Then the IO module will place the data in the data bus, and then the processor will get the data and it may store in the memory. In the context of interrupt driven IO, the processor will issue the IO command and then it may start doing some other work. Once the IO operation is completed, the processor will receive an interrupt. After receiving the interrupt, again the processor should request the IO module to give the data. Okay. So once again the IO module will place the data in the data bus, and from there the processor will collect the data and store it in the memory, or whatever operation it want to do, it will do. So in both of these cases, the involvement of processor is there for performing an IO transfer, okay, for performing an IO operation between memory to an IO device or between IO device to memory. Okay. But as we know, processor is a very expensive resource. So the time of the processor is very crucial. So is there any other way to reduce the involvement of processor in the process of IO transfer? Yes, there is a way, and that can be done by using DMA, direct memory access. So with direct memory access, data can be transferred between IO devices and memory without the involvement of processor. With direct memory access, data can be transferred between IO device and memory without the involvement of processor. So that technique is called as DMA, direct memory access. So we will be having a special control unit which can do this. So there will be a special control unit which is used to transfer block of data directly between IO device and main memory. So this control unit is called as direct memory controller. Okay, this control unit is called as DMA controller, direct memory access controller. So where this control unit will be placed, this control unit will come as a part of the IO device, right? Whatever the IO device we are using, it will be a part of the IO device. Okay, you can say it may be either a part of the IO device or it may be a part of the IO module. Okay, so it is a part of the IO device or IO module. So along with the IO device or IO module, there will be a special controller, and this controller is called as DMA controller, which can be used to directly transfer data between IO device and main memory without the involvement of processor. Okay, so if you are using that controller to transfer transfer data between IO device and main memory, that concept is said to be direct memory access. Okay. So DMA controller can perform all operation that is normally done by the processor in terms of data transfer between memory and IO device. So what are the such operation that DMA controller can do? It can provide the memory address from where the data should be read or should be written to, and also it can generate all the control signals that are required to transfer data between IO device and the main memory. Okay, so to transfer a block of data, block means collection of bytes. Okay, block means it's a collection of byte, more than one byte. So to transfer a block of data, the memory address should be incremented. That means, say for example, we want to transfer one block of data. This one block may be it may be equivalent to 4 bytes. So 4 bytes, in the sense these 4 bytes may be stored starting from the memory location 2000 to 2003. So first byte is stored in 2000, second byte is in 2001, third is in 2002, fourth is in 2003. Okay. Now after performing the first data transfer, that is after performing the data which is stored in 2000, memory location 2000 to the IO device, next it should transfer which data, which content, the content which is stored in the location 2001. So for that the address should be incremented, right? So this incrementing address incrementing logic also will be a part of DMA. Okay, that is the DMA controller can perform all operations that will be normally carried out by a processor for performing the IO operation, right? So what are the things that is done by the processor means it may have to generate the memory address from which or to which the IO transfer should be done. And it may have to generate the appropriate control signals, like whether it's a read operation or a write operation. And in case of block transfer, after transferring data from one particular address, the address location should be incremented. So all these the DMA controller will have the features. All these features will be inbuilt into the DMA controller. Okay, right. Right. Okay. So when we define a DMA, we say that the DMA is a concept of transferring data between memory and IO devices without the involvement of processor. Okay. But still there is one important thing. See, initially any program is executed by the processor, right? Say for example, CPU is executing one particular process P1. CPU is executing one particular process P1. So initially P1 may be performing some arithmetic or logical operation, some calculations it may be doing, that can be done by the processor itself, right? Say after a period of time, P1 wants to perform an IO operation. It want to write something to a hard disk, or it want to read something from a hard disk, or it want to print something, whatever it may be. Some IO operation it want to do. Okay. Now, now, now what CPU will do? If your system is having DMA capability, direct memory access capability, then CPU need not do that. It can be done by the DMA, right? But CPU should initiate the DMA. It is not DMA will happen automatically. CPU is the one which is going to initiate the DMA. So P1 says that I want to perform an IO operation. Okay, say let P1 want to write something to the hard disk. It want to write some 4 bytes to the hard disk. 4 bytes to the hard disk. Okay, right. So now CPU will initiate the DMA. So CPU will start the DMA operation. Okay, and it will say that for this particular process P1 DMA should be carried out, and also it will give the starting address. Starting, it will specify the starting address, the count, how many it will specify the starting address, okay, and the count, like how many IO transfers should be done. In this case it want to perform, and what operation to be done. It want to perform a write operation because we are writing to an IO device. Okay, so it will specify the starting address. On first IO operation should be returned to which address, say the address 5000. Okay, and count how many such operations should be done. Say count is 4 such operations should be done. And what is the operation? It is the write operation. Okay, so whatever the data which is produced by P1, the first byte will be returned to 5000. Okay, after that, after writing to 5000, count will decrement to 3. Then the next byte will go to maybe whatever may be the address. So starting address 5000 means next address will be probably 5001 or 5004 depending on the scaling factor. Okay, so then the next content will be returned to 5004. Then this count will decrement 2, become 2. Next will go to 5008, then it will decrement to 1. Next it will write to 5012, then it will decrement to 0. So when it reaches 0, then the DMA controller will understand that okay, this write operation is completed, right? So the takeaway point here is DMA, direct memory access, will be initiated by the processor. It won't start automatically by itself. The DMA also will be initiated by the processor, and while initiating, processor will give certain inputs to the DMA controller, like what is the starting address and what is the count of data transfer, number of data transfer to be done, and what operation should be done, whether it is a read operation or a write operation. After giving all these details, then DMA will take care. Okay, and processor will start doing its other work. Okay, once the DMA is completed, then DMA controller will give an interrupt to the CPU, stating that whatever the job you gave, that was done, like that. Okay, so this is the whole working philosophy of DMA, right? To initiate the DMA transfer, processor informs DMA controller the following info. It provides the following details to the DMA controller. So it means that what DMA is initiated by the processor. So what it provides: starting address, from which address the data transfer should be done. Okay, number of words, number of words, uh, number of how many words to be transferred, and direction of transfer. Direction means whether the transfer should be from IO device to memory or memory to IO device. Okay, right? So if it is from memory to IO device, that is called as read operation. Okay, sorry, if it is from memory to IO device, that is called as write operation, because you are writing to IO. Okay, if it is IO device to memory, that is called as read operation, because we are reading from IO device. Okay, so all these information will be communicated by the processor. Okay, right? Say for example, if you want to write from location 1000 to 4000 to 1004, that should be returned to the IO device. This 1000 to 1004, it refers memory location, so it is 5 locations. Then the starting address will be 1000. Number of words to be returned will be 4. Okay, and direction of transfer will be from IO. This is memory to IO device. Is it clear? So like that, DMA will provide this. CPU will provide this info, and then it will initiate the DMA. Right? Once the DMA controller completes the DMA transfer, it informs the processor by raising an interrupt. So this diagram, it shows about how, it shows the block diagram of like where the DMA controller comes. So this is the system bus. This is the system bus, which includes address bus, data bus, and control bus. Here we have the CPU or the processor. Here we have the main memory, right? Here you see there is the two disks. Okay, two hard disks are there, and these two hard disks are controlled by one disk controller. Okay, so this is not only a disk controller, but it is also a DMA controller, right? So it can be used to perform DMA operation between disk and main memory. Okay, it can be used to perform DMA operation between disk and main memory. Okay, actually it is something like this disk itself is having two DMA controller. Okay, it can perform DMA controller, it can perform data transfer between this disk to main memory, and also it can perform data transfer between this disk to main memory. Okay, and here we have a network interface card, which is used to connect this computer to other computers, okay, to the outside world, right? And this network interface card is also connected to a DMA controller. Okay, so if something is to be transferred between main memory and other computers in the network, okay, maybe that other computers may be faster than this CPU also, right? So even that operation also can be carried out by DMA. Okay, in this case, the IO device is external computers. Okay, so the data transfer between external computers and main memory can be done without the involvement of processor by using DMA. Okay, but processor will initiate it. Processor will initiate it, as we discussed earlier. Right. So this is what this block diagram shows. Fine. See, when there are more than one DMA, there may be some priority, like which should be given first priority. Okay. Say for example, there are two processes currently running, process P1 and process P2. Say process P1 want to write something to this disk. Say that we call it as disk 1, right? But process P2 want to communicate with some other system in the network. Okay, so it means there are two requests. P2 want to communicate with some other system in the internet, in the network. So there are two IO requests is coming to the CPU. One is P1 want to write to disk, and P2 wants to communicate with an IO device. Okay, so but we have only one system bus. See, we may have many DMA controllers. That is different. Okay, but all this communication, that is data transfer between IO device and memory, or between this external computers and memory, all these are carried out through what? All these are carried out through the system bus. All these are carried out through the system bus. How many system bus here we have? We have only one system bus. So this system bus can be used only by one controller at a time. If it is being used by the processor, then none of the DMA controllers can use. If it is used by any of the DMA controller, then other DMA controllers and CPU cannot use. Okay, so at a given time, only one controller can use the system bus. Okay, now initially let us assume that the bus is with the CPU. Now P1 also says that I want to write to disk 1. P2 says that I want to communicate with some computer. So now processor is the power to initiate the DMA. But what happens? This writing to this disk is controlled by this DMA, and communicating with the other computers in LAN is controlled by this DMA. Right now, a processor can give the control to only one of the DMA. It cannot give the control to both, because only one person should use the bus at a time. Okay. So now there is a question like, who should be given the control of the bus, system bus. Okay. So that will be decided by the priority. Okay. For different DMA controllers or for different IO devices, there will be some priority. Say for example, this has the priority 1, this has the priority 2, and this has the priority 3. Say the lower the number, higher the priority. In that case, bus will be given to this DMA controller. Okay, and this DMA controller, it has to wait. Once this IO operation is completed, this DMA controller will give an interrupt to the processor. After that, the bus may be given to the next DMA controller, right? So a typical system may have more than one DMA controllers. In that case, there may be priority attached with the DMA controllers. Okay, so the DMA controller or devices which are given which are having higher priority will be given access to the bus. Okay, right? But when compared with processor, DMA has higher priority. Okay, say for example, processor want to write to one of the disk, that is one or processor wants the system bus to perform some operation. At the same time, some other say for example, at the same time some other process also wants to write to the disk. Okay, right? Now there is a question like whether this is the first case is processor itself want the system bus for carrying out some operation. Okay, where DMA cannot be used, where processor should be involved. Okay, right? Say there is another IO device here attached. There is another IO device attached here. Let us call this as some IO device, say printer or something. Okay, there is no DMA controller here. Okay, so one process P1, it want to write to the printer. Right now there is no DMA controller connected with this, so it cannot be done in a DMA mode. Processor should do that. Okay, so there is another process P2. It want to communicate with the network computer. Here there is a DMA. Okay, so now uh, currently bus is with the processor, but now two process want to perform the IO operation. Now who should be given the bus, in the sense actually P2 will get the bus. I mean the DMA connected with P2 will get the bus. This DMA controller will get the bus. Okay, because now two persons were competing for the bus. Who are they? One is the DMA controller, the other one is the processor itself. So in that case, DMA controller will have the higher priority than the processor. Okay. So DMA devices are given higher priority than the processor to access the bus. That's what it is. Okay. Right. So this is the intro to DMA, and now DMA can operate in two modes. Direct memory access can happen in two modes. The first method is called as cycle stealing. The second method is called as block or burst mode. The first method is called as cycle stealing. The second method is called as block or burst mode. What does it mean? Let us discuss. Cycle stealing means cycle stealing means, say for example, uh, the DMA want to perform IO operation. Say it want to perform 4 IO operation. Okay, and the size of the IO operation is in terms of byte, in terms of bytes. Okay, that is, it want to move a byte either from memory to IO device or from IO device to memory. Like that, it want to perform 4 operations. Some process want to perform 4 operation. Okay, now what will happen? Every time, say when the processor want to perform first IO operation, I mean when it want to transfer first byte from memory to IO device or from IO device to memory, when this process say that I want to perform this IO operation, immediately CPU will what you call CPU will check, okay, this process want to perform an IO operation, so it will grant the bus to DMA. It will grant the bus to DMA for performing only one memory operation. That is, during that time the DMA can only move one byte from memory to IO device or IO device to memory. That's all. Once that is done, DMA will say acknowledgement, will send an acknowledgement. After sending the acknowledgement, bus will be reclaimed by the processor. Bus will be reclaimed by the processor. Again, when P1 wants to perform the second read or write operation, that is second byte it want to transfer from IO device to memory or memory to IO device. Once again, CPU will give the bus to the DMA. Okay, now also it will give the bus for performing only one byte of data transfer. After that is done, DMA will give an acknowledgement and bus will be taken by the processor. Okay, so again for the third byte it will happen like that. Again for the fourth byte also it will happen like that. So that technique is called a cycle stealing. So cycle stealing means DMA will be given the control to the bus only for transferring one byte of data. Okay. Okay. So DMA cycle stealing means bus is returned to the CPU after transferring every byte. Okay. Bus is returned to the CPU after transferring every byte. Again, again if the IO device, if the process want to transfer one more byte, once again the CPU will grant the bus. Again it will send acknowledgement and again it will give back the after receiving the acknowledgement, bus will be taken by the CPU. So that type of technique is called as cycle stealing. Okay. The second technique is called as block or burst mode. In a block or burst mode, the bus will be held by the DMA for for transferring a complete block. Until the complete block is transferred, DMA will hold the bus. So that is called as block or burst mode. Okay. A block may contain 100 bytes or 200 bytes or 500 bytes, whatever it may be. Okay. So CPU will give the bus to the DMA until that many block until the entire block got transferred. Okay. Once the entire block is transferred, again DMA will send an acknowledgement and the bus will be taken back by the CPU. Okay. So these are the two modes in which DMA can operate. One is cycle stealing, the other one is block or burst mode. In cycle stealing, the bus will be returned to the CPU after every data transfer, whereas in the block or burst mode, the DMA will be holding the bus until the complete block of data transfer is not done. Okay. So why we are calling this a cycle stealing? Why we say this a cycle stealing means, uh, generally the owner of the bus is processor. Okay. Generally the owner of the bus is processor. Okay. But but sometimes the bus is given to the DMA. Okay. For a short period of time. Okay. So that it is, this technique is called a cycle stealing. Cycle means bus cycle. Cycle means bus cycle. Like we are saying, cycle means a time. Okay, it's a time. It's a time duration. So it is stealing. It is as if the DMA controller is stealing the bus for one cycle. Okay, so it is called as cycle stealing. So during that one cycle only, it is performing. It is transferring one byte of data. Okay, so this is called as cycle stealing. Right. Okay. So this is about, so this is the core concepts about DMA, direct memory access. Okay. So the next subtopic in DMA, what we will be discussing is bus arbitration. Bus arbitration. Arbitration means what? Arbitration means it is something like a contest. Arbitration means it's something like a contest. So it's a contest for the bus. It's a contest for the bus. Okay. Because why there should be a contest? Why there should be a contest? Because there is only one bus. The computer is having only one system bus. Okay. Now this system bus, the requirement for this system bus is heavy. Okay. CPU wants this system bus. One is CPU want to use this system bus. Okay. That is one. And the other thing is IO devices. See, many of the DMA controller, the system may have so many DMA controllers, like DMA1, DMA2, like that it may have up to DMA-N. There may be so many DMA controllers, and all these DMA controllers may also want to use the system bus. All these DMA controllers may also want to use the system bus. Okay. So but only one of them can be given the can be granted the system bus at a given time. Okay. So how it is going to be done, that concept is called as bus arbitration. Okay. Multiple devices or multiple DMA controllers and CPU is competing for the bus. At the end of the day, who will be getting the bus, and in what process that is getting decided, that is called as bus arbitration. Okay. Fine. So the one who is having the bus right now, he is called as the bus master. Okay. The one who is holding the bus is called as bus master. Okay. So the bus master is the device that is allowed to initiate transfer on the bus. Okay. The bus master is the one who is allowed to initiate transfer on the bus. That is who the device which can use the bus, that is called as bus master. Okay. So originally CPU will be the bus master. Originally CPU will be the bus master. Okay. If some other device want to become the bus master, if some other device, say currently CPU or one of the memory DMA controller is the bus master. Okay. Then, and some other device, if they want to they want to become the bus master, then the current bus master should relinquish the bus, or it should relinquish its status. What is its status? Its status as a bus master. They should say that no more I am the bus master. Then only another device can become the bus master. Okay. Right. If device X want to become a, if DMA controller X want to become a bus master, and previously if some other DMA controller A is the bus master, then A should relinquish the bus. Then only X can become the bus master. Okay. Fine. So bus arbitration, okay, simply putting, bus arbitration is the process of becoming the bus master. Bus arbitration is the process of becoming the bus master. Who will become the bus master? That is called as bus arbitration. Right? Okay. So how this bus arbitration is done, in the sense, there are two ways of bus arbitration. One is called as centralized arbitration. The other one is called as distributed arbitration. Okay. There are two types of bus arbitration. One is centralized arbitration. The other one is a distributed arbitration. In a centralized arbitration, there will be a there will be a single bus orbiter. Okay, orbiter in the sense the one who decides who should be, whom the bus should be granted. Okay, orbiter is a device that will decide like the bus should be given to whom. Okay, so in a centralized arbitration there will be a single orbiter which performs the arbitration. Okay, there will be a single orbiter. Okay, this is a device. This can be either CPU or it can be a separate hardware logic. Okay, it can be either the CPU or it can be some hardware unit which will act as the orbiter. Okay, or it may be a, either it can be a CPU or it can be a dedicated hardware unit. That hardware unit, it will not be used for anything else. It will be used only for bus arbitration. Okay, so this unit will decide like who should be granted the bus and who should become the bus master. So that technique is called a centralized arbitration. The second technique is called as distributed arbitration. In a distributed arbitration technique, there will not be any central arbiter. There will not be any single arbiter. All the devices who want to access the bus, who want to become the bus master, all the devices who want to become the bus master will participate in a selection process. Will participate in a selection process, and 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 the result of the selection process will decide like who will become the bus master. Okay. In a distributed arbitration technique, all the devices which want to become a bus master will participate in a selection process, and the result of the selection process will decide like who will become the bus master. Okay, I think it's clear. In centralized arbitration, there will be a single central arbiter. Okay, all requests will go to him. If somebody want to become the bus master, they have to give a request to him, and finally he will decide like who should become the bus master. Okay, whereas in a distributed arbitration there is no such central arbiter. All the devices who want to become the bus master, they will participate in a selection process, and the selection, at the end of the selection process, only one device will become the winner, and the winner will become the bus master. Okay, so we'll discuss both of this technique. So this particular block diagram, actually it explains the concept of centralized bus arbitration. It explains the concept of centralized bus arbitration. Let us assume initially the bus is with processor. Initially processor is the bus master. Let us assume processor is the bus master. I am calling it as B1, BM. Say we have two DMA controllers in the system, DMA controller 1 and DMA controller 2. Okay, and there are two, these are the daisy chained line. There are two daisy chained line which is coming from the processor, and it is connected with all the DMA controllers. Here we have only two DMA controllers, so it is connected with the two. If there is more than two, it will be connected with more than that also. Okay, right. So you can see this line, the top line is called as bus busy line. Bus busy line. This is an active low signal. Active low means if it is 0, then it means it is active. If it is 1, it is not active. So it is called as active low. Low means 0. Okay. So when it is low, it is active. Okay. So this bus busy, this first line is, the top line is bus busy line. If this is 0, it means that bus is not free. Currently bus is being used by somebody. If bus is being used by somebody, then nobody can use the bus, right, at that point of time. Okay, if this is 1, then it means that bus is free. If bus is free means if somebody want to claim the bus, they can claim. Okay, that's the meaning. So bus busy will be either 0 or 1, right? If it is 0, it means that somebody is using the bus, some bus master is using the bus. If it is 1, in the sense nobody is using the bus. Similarly, the next line is BR. This is also an active low signal, which means if it is 0, it is enabled. If it is 1, it is disabled. Okay, this is bus request. Bus request. Okay, if somebody want to request the bus, they will keep a 0 here. Okay, then that request will go to the processor, right? So here you see, here we are assuming, so in centralized bus arbitration there should be a central arbiter, right? So here we are assuming the processor as the central arbiter. Processor is the arbiter. So processor is the one which will decide like who will be getting the bus. Okay, so So if DMA controller 1 wants the bus, it should keep a 0 here. Okay. If DMA controller 2 wants the bus, it should keep a 0 here. Is it clear? So this is how the concept works. Okay. Okay. Now let us assume that DMA controller 2 wants the bus, not 1. Okay. DMA controller 2 wants the bus. Okay. So it will keep a 0 here. It will keep a 0 here, and uh, let us uh, let us assume, okay, let us assume that initially, say, we are not bus busy signal, it can be either 1 or 0, whatever it may be, but it is requesting the bus. Okay, DMA controller 2 is requesting the bus. Okay, so it kept a 0. So this 0 will travel through this line and it will reach the processor, right? So now the processor understands that somebody wants the bus, but processor does not know who wants the bus, because this line you see, it is shared not only by DMA2, it is shared by DMA1 and 2. You may have more than this DMAs also, you may have 10 DMAs also. In that case, this line is shared by 10 DMA controller. Okay, so processor does not know who wants the bus, but processor knows that somebody wants the bus. Okay, then it will check whether the bus is busy or not. If bus is busy, that is if this signal is 0, then it means that somebody is already using the bus. In that case, processor will wait. Processor will wait until bus becomes free. So the moment bus becomes free, 1, okay, now the processor will decide that, okay, I will grant the bus. I will grant the bus because he is the orbiter. He is the central orbiter. So he will grant the bus. So for granting the bus, the processor, this is called as bus grant signal. Processor does not know whom to give the bus. Okay, the device which is immediately connected to the processor is DMA controller 1. So it will give the bus to DMA 1. Okay, but the request came from DMA 2, right? So it is granting the bus to actually DMA controller 1. Now the DMA controller 1 checks, there is a 1 processor is giving the bus to it, but DMA controller checks whether it has requested the bus previously or not. No, it has not requested the bus. As it has not requested the bus, it will not use this grant. It will just forward this grant to DMA 2. Okay, so this becomes bus grant 2. Okay, now this bus grant signal reaches to DMA controller 2. So now DMA controller 2 checks, okay, bus was granted to it. So it will check whether it has requested the bus. Yes, it has requested the bus. So DMA controller 2 will become the bus master. It will claim the bus. Okay, so this is the concept. This is how central arbitration technique works. So this timing diagram explains this. See, initially BR DMA controller 2 is asserting the BR signal, that is, it is enabling the BR signal. BR signal is active low signal. If it is low, it is enabled. So at this time, so this is, say we call it as some time. Okay, at this particular, say we call it as T naught. At this time, DMA controller 2 is enabling the signal. It means it is saying that I want the bus. I want the bus. Okay, that signal, it reaches the orbiter. Orbiter is currently whoever the bus master. Orbiter is, in our case, it is CPU. Okay, it reaches the CPU, right? So it reaches the CPU, right? So after it reaches the CPU, so what happens in the sense, CPU, okay, the orbiter, is granting the bus. Okay, right? Here the orbiter is not shown, but CPU is the orbiter. CPU is the orbiter, right? So once that signal reaches the orbiter, orbiter is granting the bus. Okay, orbiter is granting the bus. Orbiter is granting the bus to whom? Initially it is granting the bus to BG1, that is to processor asserts the BG1 signal. Processor is the orbiter, that is, it is giving to DMA controller 1. Okay, but DMA controller 1 so does not need the bus. So what happens? BG1 signal is propagated to DMA2. It is propagated to DMA2 as BG2, Okay, so now it is reaching DMA2, right? So now it is reaching DMA2, but it will take some time to reach to DMA2, right? Okay. So until this time, who is holding the bus? Processor is the master of the bus. Okay. Now the signal reaches DMA2. Okay. Now the signal reaches DMA2, right? So say at this point of time, the signal is reaching DMA2. BG2 is enabled here, but to reach to DMA2 also it will take some time, right? So let us assume this much time has taken to reach DMA2. Okay. Now DMA2 should claim the bus, right? Now DMA2 should claim the bus. Okay. So it takes over the bus. For taking over also there will be some time, right? For taking over also there will be some time. So it takes this much time to take over the bus. So it takes this much time to take over the bus. Now the bus is with DMA controller 2. Now DMA controller 2 is the bus master. He is using the bus, right? During this time, who is the bus master? Processor is the bus master. Okay. After this time, who is the from starting from this time onwards, who is the bus master? DMA2 is the bus master, right? Maybe DMA2 is using for some amount of time, again it is giving back to the processor, right? Okay. So during this time, during this transfer time, nobody is the bus master. During this time it is transferred from processor to DMA controller 2. During this time it is transferred to DMA controller 2 to processor. Okay. So here, even though the processor, see, you can see bus signal is 0, it is active low signal, processor is using the bus, but still it is given to DMA because DMA has a higher priority than the processor, right? So if DMA is asking, then if it is with the processor, it should be given immediately. Okay. So this is how the concept of bus arbitration works. Fine. Central arbitration. This is how the concept of centralized arbitration works. Fine. Next, let us see how the concept of distributed arbitration technique works. Okay. So with the distributed arbitration technique, each device will have a 4-bit ID number. All the device who want to become the bus master will involve in a selection process. At the end of the selection process, any one of the device will become the winner, and that device will become the bus master. Okay. So so let us discuss with that diagram, then it will be very clear. Okay. So this is the diagram. Say let us assume there are 4 devices. Okay, there are 4 devices who is competing for the bus. Okay. Say there are 4 DMA controllers. Okay. For each of them there is one line. This is for one controller, this line is for another controller, this line is for another controller, this line is for another controller. Okay. So arbitration 3, arbitration 2, arbitration 1 and arbitration 0. Okay. Right. So I mean any number of device can be there. Okay. These are the four signals. Arbitration 0, arbitration 1, 2 and 3. That this is not the number of devices. This is any device, if they want the bus, they should they should create an 4-digit unique number. They should create an 4-digit unique number, and that should be kept in this 4 lines. Okay. I mean each bit should be kept in each of the lines. Okay. The number of devices that is participating, that depends. Okay. I think it's clear. See, the point is this each device who want to acquire the bus, they should generate a 4-bit ID number. And that ID number should be kept in this bus. Okay. The 4-bit ID number, it contains what? It contains bit 0, bit 1, bit 2 and bit 3. Okay, these are the 4 bits it has. Okay, bit 3 will go to this line, arbitration 3. Bit 2 will go to this line, arbitration 2. Bit 1 will go to this line, arbitration 1. And bit 0 will go to this line, arbitration 0. Okay. If any device want to use, they will do this, right? So this is the circuit for device A. This is the circuit for device A. Okay, like that, for all device there will be a circuit. Okay, let us assume 2 devices want to compete. So let us assume two devices want to compete. So there will be device A and device B. So this is device A will generate a 4-bit number and it will keep in this 4 lines. Similarly, device B also will generate a 4-bit number. Device B also will generate a 4-bit number and it will keep in its circuit. Device B also will have a similar circuit. Okay. So there it will keep the respective bits. Okay. That means bit 3 will go to here, bit 2 will go here, bit 1 will go here, and bit 0 will go here. Okay. Fine. For simplicity, let us assume there are only two devices. Okay. And whenever somebody want to use the bus, they will activate this signal, start arbiter. This signal also will be activated. This is an active low signal, so they will put a 0 here. It means I want the bus. So device A, I mean the DMA controller A will also keep a 0 here in its circuit, right? And through that it will reach the I mean all these will be interconnected. All these devices will be interconnected, right? Device, there is no central orbiter here. Okay. Device B also in its circuit it will keep the start arbitration as 0. Are you getting? Device 0 also it will, device B also it will keep start arbitration as 0. Okay. Now there are two devices competing for the bus. Okay. So there are two devices, right? The one is device A, another one is device B. Okay. Device A is having this entire circuit in it. Device B also is having this entire circuit in it. Device A will generate the 4-bit number and it will keep in its circuit RB3, RB2, RB1 and RB0 4-bit number. Okay. And it will activate this start arbiter, it will set that to 0. Device B also will generate a 4-bit number and it will keep that 4-bit number in its own circuit. And it also will set the start arbiter line to 0. Okay. Fine. Now there will be a process of selection. By that we will be coming to know who will be given the bus. Okay. Let us assume that the 4-bit number which is selected by A is 5 0 1 0 1. Okay. 0 1 0 1 is 5, right? 8 4 2 1. This is 4, this is 1 5. Okay. Say the 4-bit number which is generated by B is 6 0 1 1 0. Okay. Now see, there are two lines. One is input line, another one is output line. Okay. This is called as input line. These 4 lines are the input line. Okay. Whereas these 4 lines are the output line. Okay. This is arbitration. This is arbitration. This is also arbitration. Okay. For each device there will be 4 input lines and 4 output line. For A also there will be 4 input line and for B also there will be a 4 input line, and I mean for A also there will be 4 input line and 4 output line. For B also there will be 4 input line and 4 output line. Okay. So in A's input line this will be kept 0 1 0, right? That is this will be 0, this will be 1, this will be 0, this will be 1, this will be 0 and this will be 1. Okay. This is in A's input line. In B's input line this will be 0, this will be 1, this will be 1 and this will be 0. Okay. What they will see in the output, in the sense both of their output will be nothing but the OR of these two inputs. So what is A's input? 0 1 0 1. What is B's input? 0 1 1 0. So you take an OR, just logical OR of this. 1 or 0 is 1, 0 or 1 is 1, 1 or 1 is 1, 0 or 0 is 0. Okay. So the output is 0 1 1 1. So that will appear here. Okay. That will appear here. Right. Here they are showing only A's. This is A's circuit. So A's number they are showing. A's number is what? 5. Similarly in B's device this number will be what? 0 1 1 0. But output will be same for both. Output is what? 0 1 1 1. Okay. Fine. Now how someone will confirm with this output, they have to confirm who will be given the granted the bus. Okay. Say let us take A. A is checking. A also will check, B also will check. So how they will check, in the sense what is A's input? 0. So the input MSB of A will be compared with the MSB of output. Is it matching? Yes, it is matching. Okay, fine. Then compare the next input. Okay, the comparison starts from MSB. Most significant bit of input and most significant bit of output will be compared. Now take the next bit and compare. Is it matching? Yes, I mean the next bit and this bit, yes, it is matching. So proceed further. Next bit, A's input is 0. Here in the output, it is 1. Is it matching? It's not matching. Whenever a not match is found, whenever a not match is found, what A should do in the sense, A should make that line as 0. A should make that line as 0. Okay. So not only that line and all the lower lines, all the lower address, it should make 0. So this input, it corresponds to which line? The higher order input, most significant bit corresponds to A or B3. Next corresponds to A or B2. So this corresponds to A or B1. Okay. The bit position at 1 is not matching. Okay, the bit position at 1 is not matching. So it will make this as 0. Already it is 0. But not only that, it should make all the lower level bits also 0. So this also will be made as 0. When you made this 2 as 0, now A's input becomes what? 0 1 0 0. So it is not no more 0 1 0 1, it is 0 1 0 0. Okay. So 0 or 0 is 0. 0 or 1 is 1. 1 or 1 is 0. 0 or 0 is 0. Okay. Now you see this is what? This is nothing but C's input. So now in output you will have this 0 1 1 0. Okay. 0 1 1 0. So in the other end C will compare. C will compare. Its most significant bit is matching. Yes. The next bit, is it matching? Yes. The next bit, is it matching? Yes. The next bit, is it matching? Yes. So who is the winner? B is the winner. So B will get the bus. Are you getting? So this is how distributed bus arbitration logic works. Right? That is, whoever the device who want to claim the bus, they will create a 4-bit number and they will keep in the respective A or B line. That is, most significant bit will go to ARB3, next will go to ARB2, next will go to ARB1, next will go to ARB0. Okay, like that every device will keep it in their own circuit, right? So that will be the input, but the output will be the exclusive OR of that, and then every device should compare their input and with the output with the respective bits. As long as it is matching, it is not an issue. Whenever there is an unmatch found, they should make the respective bit to 0 and also all its lower level bit to 0, and again OR will be calculated to find out who is the winner, and the winner will become the bus master, right? So this technique is called as uh, what you call bus arbitration technique. So whatever we have discussed, that was explained here, right? Fine. So that's it about DMA, direct memory access. Okay. So with direct memory access, the DMA controller can transfer data from memory to IO device without the involvement of processor. Okay. Fine. Let us stop here. Thank you.